how does that 3-pound lump of matter sitting inside our skulls, our brain, create something as wild and abstract as an idea? I mean, it's one of the biggest mysteries out there, right? And today, we're going to dive into a pretty radical new answer.
Yeah, think about that for a second. We've just got this web of neurons, little cells firing off electrical signals. But somehow, that translates into recognizing your friend's face, or writing a song, or that sudden flash of genius. Well, today we're exploring a fascinating theory that says the answer is hidden in the very shape of the mind.
So here's our roadmap. We're going to start with a surprisingly simple idea about shapes. Then we'll see how that idea applies to the brain's actual wiring, and from there, we'll build up to how this whole model explains learning, intuition, and even what might be a visual signature of intelligence itself. It's going to be a fun ride.
All right, so to kick things off, we've got to get our heads around a whole new way to think about structure. We're not talking about angles or lengths or measurements. Nope. We're talking about the essential stuff, the properties that make a shape what it is. It's a concept from math that might just be the key to unlocking the brain.
And that concept is called topology. The easiest way to think about it is it's the study of what makes a shape itself, fundamentally. It doesn't care how long or wide something is. What it cares about are the core properties, like how many holes it has, that stay the same even if you stretch it, squish it, or bend it all over the place.
Now this is the classic example that makes it all click. Why on earth are a coffee cup and a donut the same thing? Well, because they both have exactly one hole. You can picture it, right? You could take a clay donut and slowly, carefully stretch and mold it into a coffee cup, where the hole in the donut becomes the handle of the cup. Topologically, they are identical. That idea is going to be super important, so keep it in mind.
Okay, so donuts and coffee cups. It's a cool little brain teaser, but what in the world does this have to do with our brains? Well, this whole theory suggests that our neural networks also have a fundamental shape, and it's defined by its own kind of holes. Let's see how that works.
So if our brain's network has a shape in this topological way, what actually makes that shape? What are the holes in the donut of our mind?
The answer, according to this theory, is all about stable feedback loops. Now, these aren't physical holes you could poke a finger through. They're persistent circuits of neural activity, pathways where a signal travels all the way around and comes back to where it started. These loops are the fundamental building blocks that give the network its unique shape.
But here's the crucial part. Not all loops are created equal. You've got these temporary, unstable loops. Think of them like a circle you draw on a piece of paper. You can just shrink it down to a single dot, right? Poof, it's gone. They're fleeting connections. But then you have the stable loops. These are the ones that matter. They're like a rubber band stretched around the donut itself. You can't shrink that down to a point without breaking it. These loops are persistent, they're robust, and they form the very foundation of our thoughts.
Okay, so let's do a quick recap of the core ideas here. First, we picture the brain as a big 3D network. Second, its essential shape, its topology, is defined by those stable feedback loops we just talked about. Third, the model uses some fancier math to capture not just if a neuron fires, but its strength and rhythm too. And finally, the whole dynamic of thought is just how these signals change as they travel along those fundamental loops.
So, we've got the basic architecture down, this network with its shape defined by stable loops. But how does this structure actually do anything? Well, let's get into how this model explains one of the most basic things our brain does, learning.
So in this model, learning is really all about efficiency. When you practice something or you memorize a new fact, the neural signals for that thought get stronger, higher amplitude, and they fire more often. And these superpowered signals start to basically carve out the most efficient highways through that complex road network in your brain.
And this is where things get really cool. For these strong, practiced signals, the brain's overwhelming complexity kind of just melts away. They don't see the tangled mess of every possible connection anymore. Instead, they start to see a much cleaner, much more direct structure.
This whole process is called degeneration. Now, that sounds complicated, but it's really just about simplification. A signal starts out in this dense, messy web of possibilities. But as you learn, as you practice, that web degenerates into a super efficient tree. And the endpoints of that tree, those are distinct categories. This is literally how your brain learns to tell the difference between a chair and a table. It creates a separate, stable branch for each one.
Okay, so that's learning.
It's about strengthening pathways, getting better at sorting things we already know. But what about that sudden flash of insight, that aha moment that comes out of nowhere? Well, believe it or not, the model has an explanation for that too.
And I think this distinction is just beautiful. Learning is all about reinforcing the tree you already have. You're making the branches stronger. But intuition, oh, that's something way more radical. Intuition is when you change the fundamental relationships between the loops themselves. You're not just strengthening the tree, you're warping and deforming the entire structure, creating totally new branches, totally new endpoints. It's not just learning a category, it's inventing one.
All right, we are now getting to what I think is the most mind-blowing part of this whole theory. If learning creates this tree structure, is there some kind of sign? A way to tell when the process is actually complete? Is there a visible pattern that just pops out? To put it another way, if a network has truly mastered something, if it's learned all it can, does it leave behind a signature, a kind of geometric calling card that says, yep, I understand this now?
And the answer, which is just incredible, is yes. When a network has fully sorted out all of its information, the endpoints of its learned tree, those distinct categories it created, they don't just sit there randomly. Nope, they arrange themselves into a very specific and, frankly, very beautiful shape. And that shape is a fractal. You've definitely seen these before. They're those infinitely complex patterns that look similar no matter how far you zoom in. Think of a snowflake or a bolt of lightning. They're made by repeating a simple process over and over and over again.
And this, right here, is the big payoff. The endpoints of that fully learned classification tree arrange themselves into a closed fractal curve. This isn't just a coincidence. The math says it has to happen this way. According to this model, this beautiful, infinitely complex pattern is the literal signature of a completed learning process. It is the geometric sign of intelligence.
And the implications of this are, well, they're huge. This is a perfect example of what philosophers call top-down causation. It's not just that individual neurons firing create a mind, it's that the overall topological shape of the mind, that system of stable loops, is actually controlling and directing the behavior of the individual neurons. The whole is truly, literally, guiding its parts.
Which brings us to this absolutely stunning final thought from the author, that from these simple, almost mindless mathematical rules about shape and feedback and signals, something as complex and seemingly magical as a mind can just emerge.
So I'll leave you with this to think about. If our minds are governed by this hidden geometric logic, what else could be? Could the booms and busts of our economies, or the delicate dance of an ecosystem, could they also have a hidden topological shape, a fractal signature, just waiting for us to find it?